How does signal processing turn noise into control for BCI performance? Imagine trying to listen to a friend in a noisy room. Your brain filters out the background noise so you can focus on what matters. That's similar to what signal processing does in brain-computer interfaces. It takes the brain's electrical signals and cleans them up so they can be used for control. Brain signals are complex and often mixed with unwanted noise from muscle movements, eye blinks, or even electrical interference from nearby devices. Without cleaning these signals, the system would be unreliable and hard to use. The first step in signal processing is capturing the signals. Sensors placed on the scalp, inside the skull, or directly on the brain's surface record electrical activity. Electroencephalography is a common non-invasive method that captures signals from the brain's surface. Once recorded, these signals go through several processing stages to make them usable. The initial stage is noise reduction. This involves filtering out unwanted signals. For example, bandpass filters allow only the frequencies associated with brain activity to pass through. Techniques like independent component analysis or adaptive filtering help identify and remove artifacts caused by eye blinks or muscle movements. These methods help isolate the brain's true signals from the noise. Next, the signals are normalized. Normalization adjusts the data to make sure it's consistent across different sessions or people. This step helps the system interpret signals accurately, even if the brain activity varies from person to person or day to day. It creates a common baseline so the system can compare signals reliably. After normalization, the system extracts features. Features are specific patterns or characteristics in the signals that relate to the user's intentions. These might include changes in frequency, amplitude, or the spatial distribution of signals across the scalp. For example, imagining moving a hand creates distinct patterns that can be identified during this step. The final step is classification. Machine learning algorithms analyze these features and decide what they mean. For instance, they can determine if a person is thinking about moving their left or right hand. Once classified, these signals are translated into commands that control external devices like robotic arms or computer cursors. This is how thought becomes action. Signal processing is vital because it makes brain signals reliable and fast enough for real-time control. Without it, the noise would drown out the meaningful signals, making control impossible. With effective processing, brain-computer interfaces can help people with paralysis communicate, control prosthetic limbs, or even interact with computers just by thinking. It turns the brain's electrical chatter into clear commands, opening new doors for human-machine interaction and neurotechnology.